Hi everyone, my name is, as Andrei has introduced me, Alexander Azimov. I'm doing some monitoring and transport infrastructure for Yandex, and today I will tell you how to make unique features for your network. In case there are some spine problems, this network could heal itself. And what role the label will play. For those who do not know, I will give a detailed introduction for many network engineers. Data center network starts with store, with the rack. Usually, TOR has connection to the spines. These connections usually are deemed equal, and between the uplinks, you will use hash in order to balance it, including proto and different IPs. So there are no surprises there. Then let me speak about the architecture of labels. So the spines of the first level are not connected between themselves and actually are connected by means of superspines. And X will stand for superspine, just for practical purposes. And it's obvious that, on the other hand, we have TOR connected to the spines of the first tier, and what is so important about that picture? If we have interaction within the rack, then interaction is done through TOR. If the interaction goes within the module, then it goes through the spines of the first tier. If the interaction goes between the modules, then we have TOR number 2, and that means that actually the interaction will go through the tier 1 and tier 2. Academically or theoretically, such an architecture is very much scalable once you have port capacity. If you have some empty room in data center and fiber optics, you can increase the number of tiers and increase the overall capacity of the network. Actually, it's very easy to be done on paper. I will not speak in more detail about that. So I'd like to make right conclusions. We have one data center and many routes which are independent. One route actually is available only within TOR. Within the module, the number of paths equals the number of planes. Between the modules, the number of paths equals superspines multiplied by the number of spines. And to make it easy for you to feel the scale, I will give you the figures which are true for the data center. So there are 8 planes with 32 spines within each. So it means that we have 256 intermodular interactions. If we develop a data center, a failure-free data center, a self-healing data center, then the plane architecture is the right way to do. Because therefore you can address the scalability problem, and there are multiple independent paths, and the question remains how such an architecture may live through the failures. They might be different failures, this is what we're going to discuss. But for instance, one of the superspines has failed, and I will get back to the double plane architecture because it would be easier for us to understand what is going on. X11 is ill. How will it affect the services which are living within the data center? A lot would depend on how the failure looks like. For instance, if it's a good and profound healer, so actually if this failure can be captured by the automatics, and if the automatics would isolate the nodes, then the traffic will be rerouted to the alternative path, and the services will not notice anything. This is the best case scenario. The bad case scenario is when we have losses and when the automation doesn't notice the problem. In order to understand how it may affect applications, we'll have to spend time on looking at how TCP protocol works. I think that I will not shock anyone that TCP, this is when the transmission is acknowledged or confirmed. So the sender sends 2 packages and would get a cumulative act that I have received 2 packages. After that, actually, the sender sends 2 packages more, and the situation would replicate. So this is with a little bit of simplification. So the scenario is true once the number of packages equals 2. On the fly, I mean. And we'll continue to speak about the resending of packages, but in essence, the window doesn't affect it. What will happen if we have lost package number 3? So in that case, so the receiver will get the packages number 1, 2, and 4, and using SIK option, he will inform the sender that 3 packages were received and number 3 is lost. And the sender, at that moment of time, with no problem will repeat sending of the lost package. But once the lost package is lost, number 4, the situation would be totally different. The receiver will receive the first 3 packages and actually would start reading immediately through the optimization of TCP format. He will not anticipate the final package once there is no notification that there should be 4 packages. And after some time waited, he will send a notification of the receipt of 3 packages, and the sender will also wait until the 4th package is delivered and not to overload the network. He will wait until the system actually informs him that something is lost. RTO stands for certain constant figures. What is important that if we are unlucky and the 4th package is lost once again, then RTO would double. So every failed attempt doubles the RTO. So let's look at how RTO looks like. By default, the minimum RTO equals 200 milliseconds. And this is a minimum RTO for data packages. For scene packages, it equals 1 second. You may see that the very first attempt to resend the package will take 100 times more than the RTT time within data center. Let's get back to our scenario. What happens within the service? The service is losing the packages. So initially, it is lucky enough that something is lost within the window. It would get a SAC and would confirm or resend the packages which were lost on the way. But if the unlucky cycle goes on, the RTO takes place, and what is so important there? Really, we have a lot of paths within the way, but PTC traffic will go through the same failed stack. So it means that under the condition that X11 is not healing itself, will not result in rerouting of the traffic. We'll try to deliver the package through the same failed node, and it will actually result in a domino effect. There will be a lot of interacting applications and a number of TCP connections. Almost all the applications available from the data center would erode, and following the proverb that actually once you fail to put the shoe on the horse stumbles, and once the horse stumbles, you lose the war. And this erosion which affects the services, means that the users will fail to receive all the information, and the retention time would increase. There are two classical solutions, textbook solutions. First of all, this is about services. The services which try to be on the safe side and solve the problem by means of mending the TCP stacks, or make timeout at the level of the application, or make TCP sessions reuse with software-defined health checks. But the problem is that such solutions are not scalable at all, and B, they are not checked and verified. So if certain service by chance would actually configure the options and applications the way actually it's good, it would not be applicable to all the applications and for all the data centers. And secondly, the service will not understand what was done correct and what was done not correct. So it was done poorly and not scalable. If a network problem arises, who is to be blamed for that? Certainly it would be NOC to be blamed for that. What NOC does? Well, at least many services believe that the work is done like that within the NOC, but frankly speaking, this is only a part of the approach. NOC, according to the classical way, also does a lot of monitoring, so black box monitoring, white box monitoring. Black box monitoring was dwelt on by Alexander Klimenko at the previous Next Hop. But he used a spine as an example. But an ideal monitoring will have certain time lag, usually several minutes. After, actually, it turns on, the network engineers will take time in order to recheck everything, localize the problem, and somehow solve the problem. So the healing will take 5 minutes in best case scenario, or in worst case scenario, actually it will take about 20 minutes. Obviously, all that time, 5 to 20 minutes, will have service degradation, which probably is no good. And something which we would like to get is that we have so many paths, and the problem arises because TCP flows use the same path, and we need something in order to use multiple paths within one TCP connection. Similarly, we have a solution. We have TCP, which is called multipath TCP. But it was developed for a totally different purpose. It was designed for iPhones. I apologize. For smartphones, not for iPhones, certainly, which have several network devices. And in order to maximize the data transmission or to make a primary backup regimen, a mechanism was designed which is absolutely transparent for applications, creates multiple paths, and in case of a failure, you may switch between them and optimize the band. But there are some nuances. In order to understand these nuances, we'll have to look at how the flows work. So the flows are structured hop by hop. And here a problem arises. If the first flow doesn't install well, the flow number 2 and number 3 will never be installed, will never merge. So it now means that multiple TCP does not address the problem of failure of the first flow. So if actually the first flow goes down, the multiple TCP turns into ordinary TCP, and therefore we cannot take advantage of the multiple paths. What can help us? Some of you probably have already guessed that an important role would be played by IPv6 header. Actually, it is not available within v4. It takes 20 bits. And there were some debates about how to use that properly. So the debates were going on, something would be recorded, and Linux Nucleus did something which is off record, and will tell you what was done. But to begin with, let us do a little bit of investigation. I will tell you what was done to Linux nuclei within several years. So 2014, an engineer from one big and respectful company adds a dependence of low label on socket hash. So what they try to mend, this is actually has something to do with RFC 6438. Very often within the nucleus, we encapsulate IPv6 and IPv4. And for some time, there were problems with switches which could not look into two headers in order to get to TCP or EDP and to find appropriate ports. And it turned out that the hash, if you look at the first two IP headers, they are fixed. In order to avoid that, in order not to jeopardize the balancing, they suggested to use hash of 52PL into the header. The same was done for other encapsulation schemes for UTP. This way or another way, the purpose was quite obvious, and it was quite useful exercise for that period of time. In 2015, the same engineer actually offered a new patch, and it looked very interesting. So it says that we will randomize hash in case of negative event on the root. What a negative routing event is? This is RTO, which we have discussed before. This is a loss of the window host, and the event is really very negative. And it would be quite difficult to guess that it is what caused the failure. 2016, another esteemed company, a big one actually, collects the lost scratches and makes sure that this hash, which we have randomized now, is retransmits on every sync ACK. And the final objective is to make sure that the traffic, in case of losses, overloading of connections, could reroute.
Of course, after that, there have been many publications that you can find easily. Well, actually, you can't find them because there has been no publication on the subject at all. But you already know a solution. If you haven't fully understood what has been done, I will tell you now. To conclude about what has been done, what functions have been added to the Linux core. SKTX hash is randomly changed after RTO. That's the negative result of routing. The hash depends on this TX hash, and the flow label depends on the back hash, or the SKB hash. There are some functions here which I couldn't actually put on this slide, but you can check them later. What is important here is the value of the flow label field, which has a random meaning, and as a result, this influences our unhappy TCP flow. If there is a SAC, then we can't do anything. We are trying to resend this message, but right now it's okay. But in case of RTO, and given that we added the flow label function, the traffic can go via another route. And the more nodes we have, the more likely it is that there will be no problem because of a failure of a particular device. There's just one problem remaining, RTO. Of course, we can't find another route, but we spent too much time on this. 250 milliseconds is too much. I told you about timeouts. Actually, 1 second of timeout is too much for a server. It can make it fail. And given that the real RTT is about 1 millisecond, 200 milliseconds is too much. So how can we reduce RTO timeouts? There are timeouts that are responsible for RTO if data is lost, but we can recover it because there is the IP function, and one of its parameters has this RTO min. Of course, we shouldn't amend the RTO on a global scale, but only locally. So this is a working mechanism. But SceneRto is harder to improve because it's like nailed there to a certain place. So it's very difficult to change it. But there is one way. We can use the EBPF. To put it simply, EBPF are small C software products which can be installed on laptops as stacks and CP stacks. And with them, it is possible to change a lot of settings. Actually, it's a long-term trend. Instead of dividing the IP function into many different parameters, we can shift towards EBPF. And by means of EBPF, we can actually amend the congestion control or other settings of TCP, various settings. But what is important is that we can use this function to change SceneRto. And you can see a link here. It is open information. And this is a working example, a very rough one, but it means that within this data center, we compare the first 44 bits. So if the IP addresses coincide, then it's OK, and we don't change the value of SceneRto timeout. Of course, we could do the same thing more elegantly. This is just an example, which is pretty simple. What do we already know? We know that this architecture is scalable. It is extremely useful if we switch flow label on the TOR, and if we have the possibility to avoid the problem sections in order to decrease RTO and SceneRto. It's the easiest way to use EBPF software. But there is a question. Is it safe to use a label for balancing? And actually, there are some fine points here. For example, you have a service in your network. Unfortunately, I don't have the time to explain what Unicast means. But Unicast is a server which is actually located on different servers. And there might be a problem because there is an RTO event which can arise not only when traffic goes via the factory, but this problem can also arise on the TRO buffer or on the host. And in this case, we have an RTO event, and it changes the flow label. And in this case, the traffic can go to another unicast. And if it's a stateful unicast, it's in a particular connection state. Maybe there is a particular server, and there is a problem there. Because after the RTO, the connection goes to a server which doesn't know anything about this connection. If we don't have any advanced servers or cast servers, then this traffic will just fail and the connection will break. So what can we do here? Within your controlled environment, where you do the flow label balancing, it is necessary to fix the flow label value when you go to EK servers. You can use it with the same EBPF software. But the important thing is that it needs to be done. But what can you do if you are not a data center operator, if you're a communications operator? It's also your problem, because starting with some versions, Juniper and Arista, for some unknown reason, put the default function of the flow label. As a result, you will disconnect the TCP of users using your network. So I recommend you strongly to check the settings of your system. Well, anyway, I think all of you are ready to listen to how it actually works. After we got the flow label on TORs and we prepared an agent which now lives on hosts, we decided not to wait for the next default, and we took a TOR with 4 uplinks. And we did a drop on one of them. And actually, we made it lose all the packages. And you can see that on the left, we have the first package monitoring, which went down to 75%, because 25% of the packages are lost. On the right, you can see the charts for servers that are after this TOR. They are connected within the rack, and you can see that they went even lower. Why? Why did they drop even more than by 25%? In some cases, it's by 3 or 4 times. These are those application timeouts with this unhappy connection, where try to send the data through, and the whole system is waiting for a response within this data center. And we sent a request to a number of sources, and we are waiting for them to send some information, and the system is idle. It's really bad. And now we are having the same experiment, but with the flow label value on. As you can see on the left, our package monitoring dropped by the same 25%, which is logical, because this system just calculates the number of packages delivered and lost. And on the right, we have the service chart, and here you will not see the effect from the problem stack, which means that within milliseconds, the traffic flowed from the problem part to the 3 remaining uplinks, which are unaffected. And as a result, we have a self-healing network. Well, that was my last slide, and now I would draw some conclusions. I hope that right now you know how to build a data center network which is self-healing. And for that, you will not need to go to the archive of a Linux core to look for patches there. Flow label is a solution here, but we need to be careful about it. I emphasize once again, if you are a network operator, you should not use it as a hash function, because then you will disrupt your user's session. There is a conceptual switch that network engineers should do. They should understand that it all starts not with TOR, but with the host. And then we need to change the RTO towards Unicast servers. I think it's a good example showing why it is. It all starts with the host and not with the network device. And the mechanics of the flow label is working for other administrative segments, such as the RTC traffic, and we can use it in order to control the outgoing traffic, but this is what I'm going to tell you next time. Thank you very much. If there are any questions, I am ready to answer them. Thank you very much, Alexander. That's been a very interesting presentation. Actually, we need network engineers to control the hosts. Unfortunately, we don't have any time for any questions. But Alexander, will you please answer the questions in the chat?